Okay, welcome back then everybody. And yeah, we're now on the fifth part of these lectures, so hopefully you're keeping up and you're having a go at the mechanisms and the exercises that I've asked you to have a look at. So I've just, as a recap, put on here the E2 mechanism that we were considering in the last lecture, because what we're going to be moving on to do is to think about the stereochemical outcomes of this. So just to remind you, for the E2 reaction, it's bimolecular. So that means we have two molecules involved in that rate determining step. We've got our base pulling off the hydrogen at the same time as that bond breaks and pushes electrons in to make the double bond, at the same time as the leaving group departs. And so it proceeds via transition state to give our alkene, the base with the hydrogen and the leaving group. So what we're going to do now is think again about the stereochemical outcomes. Are we going to be able to make a single isomer of alkene, or are we going to make a mixture? You know, these are the considerations that we have when we look at the elimination mechanisms, remembering that different isomers can have different biological and therapeutic properties. So when we think about this elimination occurring, what we find is we have to think about the orbitals and how they're going to align in that transition state as we go from our starting material through to our alkene product. So because we're making a double bond, we're making an alkene pi bond, what we need to do is to have the p orbitals in a planar arrangement, so that if they're in the same plane, they can overlap during the elimination to give the extra overlap given the double bond, the alkene. So for the p orbitals to be able to be in the same plane, what we find is that the hydrogen that's coming off the two carbons which are connected, which are going to become the double bond, the Y, and the base, all of those should be lying in the same plane during the elimination so that those orbitals can overlap as the new bond forms and the H plus and the Y minus depart. So that will give maximum overlap of the orbitals, which will mean that the formation of the pi bond is pretty straightforward. So when we think about that, when we think about the elimination, we have to think how can those these particular groups, the CB, the CA, the H plus, the Y minus and the base, how can they actually be orientated so that they are in the same plane? And there's two ways that we can do that. They could be anti to each other, but in the same plane, or they could be syn to each other. And I've got that more clearly on this slide. So when we're thinking about the stereochemistry and what's going to happen, what we're saying is we need the H, the CC bond and the Y to be in the same plane so that we can get the overlap of the p orbitals to make the double bond. But there's two ways that they could be in the same plane. So here they're in the same plane and the H here is up and the Y here is down, so it's anti. So this would be anti-periplanar. Or we could have the H, the C, the Y. Again, they're all still in the same plane, but now the H is on the same side as the Y. So these are called syn, S-Y-N, syn periplanar. So when we look at this elimination, we can be thinking about elimination of the hydrogen to make the double bond and lose the Y in this anti-periplanar arrangement. Or we could be thinking about loss of the hydrogen, pushing the electrons into this double bond, losing the Y in this syn periplanar arrangement. So one of them might be more stable than the other, and if it's more stable, then we're going to get the product which is formed from that one. So if we were to think about these two arrangements where the groups are planar, but here they're anti and here they're syn, what we can do is think about the stability of the two in terms of sterics and electronics. So what we can do in particular is if we were to look at this one here, which is the anti one because this is up and this one here is down, we could imagine if we were looking along this bond here, where are the groups at this front carbon relative to the groups on the back carbon? And we can draw that via this this depiction here, which we call a Newman projection. I'm going to go through it on this slide, but again, there's one of these walkthrough videos where I draw it out in real time. So go through that again, just to get extra clarity, because this is quite a difficult concept. So let's imagine then we're looking along this bond here and we're seeing where are the groups here relative to this one here. Well, on this front carbon, we've got a hydrogen, we've got an R to the left and an R1 to the right. So these are just any substituents. We're not stipulating what they are, but we're saying we've got R to the left as shown here, and we've got R1 to the right as shown here. Now, if we were looking along that carbon-carbon bond, we'd also see these groups here on that back carbon, and we'd see where they are relative to the groups on this front carbon. So in this depiction here, we've got our front carbon with the groups we've just gone through. And then on this circle at the back, we're saying these are the groups which are coming off of this back carbon. So again, we've got an R with 2 dashes to the left. So put that there to the left. We've got an R with 3 dashes to the right. So put that to the right. And we've got the Y just sticking down, just sticking down. So when we do this configuration, remembering that what we're doing is we're looking along this bond here, we see that every group here is lying between the groups on that back carbon. So it's what we call staggered. They're not in front of each other, they're staggering each other. So each one here, so here and here, we've got this in between. Here and here, that's in between. Here and here, that's in between. So it's staggered. So that's what we would draw to demonstrate this one, where these are in the same plane, but they're anti-periplanar. So now if we were to look at this alternative, where we said these were syn periplanar, SYN, syn periplanar, because they're both on the same side. So if we were to again look along this bond here, on this front carbon, we'd have our hydrogen sticking up, as shown here, our R to the left, our R dash to the right. But when we look along that carbon-carbon bond, what we now see is that Y is also sticking up in the same area of space as that hydrogen. So we've got that sticking up on the back. The R triple dash is coming to the left, so that's to the left, and the R double dash to the right, So in this syn, if we look down this bond, as shown in this Newman projection, what we see is every bond here at the front is basically eclipsing. It's in the same area of space as the one behind. So this is eclipsing, H is eclipsing the Y, R is eclipsing the R3 dash, R1 is eclipsing the R double dash. So this is staggered and this is eclipsed. Okay, I just got that the wrong way around. So forget that. This one here is staggered, this one here is eclipsed. And what you can imagine is the staggered one is going to be much more stable because all of these bonds with their electron density is lying between the other bonds with their electron density. So this is going to be much more favoured from a size, a steric point of view, and also from electronics compared to the eclipsed. So why are we saying this? We're saying this because when we do our elimination, we are going to do the elimination from this anti-periplanar setup, because then when we've got these staggered relative to each other, we've got a much more stable form here. We don't get so many steric or electronic interactions as we would with the eclipsed. So this one here will be more favoured. So the anti-periplanar elimination is favoured. So that means when we've got this is exactly what we had before. So it's exactly what we've got here. What we're saying is when our base now comes in to do the elimination in that one-step reaction where the base pulls off the hydrogen, kicks electrons in to make the double bond and loses the leaving group via a transition state. If this occurs via the anti-periplanar arrangement, which we've said was more favoured here. So when that occurs, because in the transition state, these groups here on the carbon at the back relative to the carbon at the front is defined. Again, the substituent here on the carbon at the back is defined relative to the substituent at the carbon at the front. That means because all of the bonds are breaking and forming at the same time, we're going to get one alkene of product, where the stereochemistry here of the alkene, the relative positions of these groups relative to these groups, is going to be dictated by their position here. And that's going to be dictated by the stereochemistry of the starter material and when we put the groups in the anti-periplanar arrangement. So what that means is we get a very stereospecific reaction for E2 eliminations, for these elimination bimolecular reactions, where the stereochemistry of the starter material will influence the stereochemistry of the product, and we're going to get the elimination through these anti-periplanar staggered conformations. So what that means in terms of the stereochemical outcome is it's stereospecific. It's very specific. You're only going to get one isomer or product as a direct result of the mechanism of the reaction and the stereochemistry of the starter material. And we'll see a minute on the next slide how this works out, how one isomer gives one isomer of product, whereas a different isomer of starting material could give a different isomer of product. But the key thing is it's stereospecific. So learn this definition. A stereospecific reaction is one that leads to the production of a single isomer of product as a direct result of the mechanism of the reaction and the stereochemistry of the starter material. And this is what we see for the E2 reaction. We will have one isomer of starter material. When it goes to the anti-periplanar arrangement, that will give us one isomer of product. So the stereospecific reaction is very different to a stereoselective reaction. So for a stereoselective reaction, you might get one predominant product, but you'll always get a mixture because the reaction pathway has a choice. So if we were to think back to the E1 reaction, if you remember, we found that we did get one predominant product, but we always got a mixture of the E and the Z alkenes. And that was because the reaction pathway had a choice. The carbocation intermediate from which the elimination occurred could rotate around the CC bond to give different orientations of that carbocation, and they led to the different alkene stereochemistries. So learn the definitions for stereospecific and stereoselective. Stereospecific will apply to E2. It also applies to SN2. Stereoselective will apply to E1. In this case, it will not apply to SN1 because in SN1 we don't get one predominant product, we get a racemic mixture. So let's have a look at a specific example just to demonstrate how, if we have one isomer of starter material in the E2 reaction, because it's stereospecific, we will end up with one stereoisomer of the alkene product. Whereas if we had the different isomer of starter material, we would get the different isomer of product. So I'm going to go through this, but again, please do have a look at this additional video where I go through this in on paper, because I think that will help you to see what I'm drawing in, what bonds are breaking, which bonds are forming. It's exactly the same material, so it's just a case of giving you a second chance to go through it and understand the concept. So we're exemplifying the stereochemistry of E2 reactions, and we are demonstrating that they are stereospecific, i.e. one starting material isomer would give one isomer of alkene, a different isomer of starting material would give a different isomer of alkene. So first of all, let's just look at these. These are our starter materials, and these are diastereoisomers. So to remind you from Dr. Sarah Allman's course, a diastereoisomer is a stereoisomer which is not related as object and mirror image. If it was related as object and mirror image, that would be an enantiomer. So here, this bond here, or this carbon here, has got the same stereochemistry as this one. This one here, though, in contrast, here our methyl is pointing away from us, as opposed to this one, which is pointing towards us. So these two are stereoisomers. They are not related as object and mirror image, so they are diastereoisomers. So in shorthand form, we don't always draw in all of our hydrogens, but in this case here, where we're going to be doing the elimination reaction, obviously we need a hydrogen involved in that, because in the elimination we lose hydrogen and a leaving group. So it's helpful to add the hydrogens in. We're just going to go through this example first, and then we'll do exactly the same for this. So if you're going to add the hydrogens in, remember these carbons are tetrahedral and they've got 4 groups attached to them. So if we haven't drawn all of the 4 substituents in, the missing one is a hydrogen. And remember, because they're tetrahedral, that would mean that the hydrogen is in the other tetrahedral position. So here we've got a phenyl, we've got a carbon-carbon bond, methyl is up. That means hydrogen here would be pointing away from us. Here, this is the other one where we've got a hydrogen. Here the bromine is up, so the hydrogen would be away from us. So on this walkthrough video, I show that to you. What we need to do, though, is remember that in our E2 elimination, we want our hydrogen and our leaving group to be anti-periplanar. So they have to be in the same plane, but they have to be pointing away from each other. So this orientation, if you had a model and you had this molecule in front of you, you would see that if you rotated around that carbon-carbon bond to put the hydrogen at this position and the bromine anti-periplanar, you would end up with this. So as I say, on the walkthrough video, that will be clearer because I'll have the hydrogens drawn in these positions, and you'll be able to see that if you rotate around that bond to get the hydrogen and the bromine anti-periplanar, we end up with this orientation. So then our base will come in and it will remove the hydrogen at the same time as the electrons will feed in, at the same time as we break off our leaving group to go through a transition state. And the stereochemistry here in this anti-periplanar arrangement is what will influence the stereochemistry here of the alkene. So for instance, if we were to look here, when our elimination occurs in the transition state, this phenyl here is pointing towards us, whereas this one here with the dashed bond is pointing away from us. So they are on opposite sides. So in our alkene, they are going to be on opposite sides. The same is true here. This methyl group here is away from us. This hydrogen group here is towards us. So again, in the alkene, we're going to have the methyl on one side and the hydrogen on the other. So have a look at the walkthrough video, maybe have a look at that to go through this example before you have a look at the second example, because maybe if you've then understood that, you could have a go at writing this out real time without looking at the second part of that video, and then you could use that to check your answer. Okay, so pause your lecture, have a look at this and check that you're happy from what I've just explained and from what you see in the walkthrough video, that you understand this part here and how the stereochemistry of the starter material influences the stereochemistry of the molecule when it's got the hydrogen and the leaving group anti-periplanar, and how the stereochemistry of that will therefore influence the transition state and hence the stereochemistry of the product. Okay, so if you've had a go at the second one, let's run through this. So what we would see here is exactly the same. We've got hydrogens on these carbons to make them up to tetrahedral. So here, if the methyl is away, the hydrogen will be towards us. Here, if the bromine is towards us, the hydrogen will be away. And when we rotate around this bond to put our hydrogen at this position and the bromine here anti-periplanar, because that's the most stable arrangement for the E2 due to steric and electronic minimizations, then we end up with this structure here. So our hydrogen and our bromine are anti to each other. So again, when we do our elimination, when a base comes off, pulls off the hydrogen, feeds the electrons in, kicks out the bromide, when we do this via the transition state, the orientation of the groups in this transition state will influence where they are in the alkene. So again, let's have a look. We've got a phenyl on this carbon and a phenyl on that carbon. Both of them have got dashed bonds, so both of them are going to be pointing away, both on the same side. So here we've got our phenyl and the phenyl, they're both on the same side because they're both pointing away. Here we've got the methyl is up, the hydrogen is up, so the methyl and the hydrogen will be on the same side. So if we look, this is obviously a different isomer to this. Here we have the phenols on opposite sides. Here we've got the phenols on same sides. So this alkene is a different isomer to this one. This starter material was a different diastereoisomer to this one. So what we've exemplified here is that in the E2 reaction, if you have one isomer of starter material, you get one isomer of product due to the mechanism of the reaction, the fact that it occurs through the anti-periplanar arrangement. If we had the different isomer of starter material here, we ended up with a different isomer of product, again due to the reaction mechanism that occurs through the anti-periplanar arrangement for the transition state. Okay, so that's really important that you hopefully understand that the E2 reaction is stereospecific. It leads to the production of a single isomer as a direct result of the mechanism of the reaction and the stereochemistry of the starter material. Remember that the SN2 reaction is also stereospecific. In that case, we get inversion of stereochemistry. Remember that the E1 reaction is stereoselective and that the SN1 reaction is neither stereoselective nor stereospecific because it leads to a mixture, a 50-50 mixture of the enantiomers. Okay, so we're just going to finish this part by again sort of saying E1 or E2 mechanism in the way that we looked at SN1 and SN2 mechanism. Why does it matter? Well, it matters because we've seen in E1 we're going to get a mixture of isomers. One might predominate, but we're going to make a mixture. Whereas in E2 we're going to get a single isomer of product. So that's important in our drug discovery because we might want a single isomer if we know that's definitely the one that we need for the best activity, or we might need to make a mixture so that we can work out which one is the best, or maybe it doesn't matter. Maybe they both have the same activity for that particular therapeutic application. So if it's important that we know, maybe sometimes we want to do an E1 reaction, sometimes we want to do the E2 mechanism, then we can think about factors that will promote the E1 as opposed to the E2 reaction. And again, this is recap really from what we saw when we looked at SN1 versus SN2 reactions. So the reason we're able to recap and draw out similar features is because the mechanism of the E1 is similar to the SN1. The mechanism of the E2 is similar to the SN2. So why are they similar? They're similar because in the E1 and the SN1, both of the rate determining steps involve loss of the leaving group. The E2 is similar to the SN2 because the rate determining step for each of these involves the nucleophile or the base attacking the substrate at the same time as the leaving group departs. So if we know that for E1 we're going to form a carbocation, then if we can form a very stable carbocation, then that will favour the E1 reaction. So if you were to look back at your SN1 notes, you would see that there were certain factors that could affect the carbocation stability. So for instance, hyperconjugation would make a tertiary carbocation more stable than a secondary than a primary, and also resonance could help to stabilise that carbocation. So if you've got a stable carbocation, it's going to favour an E1 reaction. We looked for SN1 and SN2 at the nature of the solvent because that can help to stabilise particular species. And so as we saw for SN1 reactions, if we have a good ionising, iron solvating medium, that will favour the E1 reaction because it goes through a real charged carbocation, but it would have very little effect on the E2 reaction because that goes through a transition state. Because the rate equation for the E2 reaction involves the base, in contrast to the E1, which doesn't involve the base at all in that rate determining step or in the rate equation, we find that for E2, where it is involved in the rate determining step, if we have a strong base or if you have a high concentration of base, that will enhance the E2 reaction, but it would have no effect on the E1 reaction. For SN1 and SN2, we also considered steric effects in terms of how easy it was for the nucleophile to approach the carbon, because if it was easy to approach the carbon directly, then an SN2 reaction would be more likely. But if it was very sterically hindered, it's more likely we'd need to lose the leaving group first to give a less sterically hindered carbocation. We don't have such a big discussion of that in the elimination reactions. The reason is that for the elimination reactions, our base is attacking a hydrogen, which is on the outside of the molecule, rather than having to penetrate through and get to the carbon, which would be more sterically hindered. So the steric effects are far less pronounced for the elimination reactions, and it's not something that we consider when we want to influence E1 or E2 mechanisms. Okay, so that's going to be a good place for us to stop today. We've covered most of the main material, and the final lecture that I will give will be looking at elimination versus substitution reactions, because remember we've said that these are competing reactions. So whereas we've now seen how we could favour SN1 over SN2 and vice versa, and we've looked at E1 versus E2 and vice versa, the one thing that will be left for us to do is to think, well, how can we actually favour elimination as a mechanism over substitution and vice versa? So we'll leave it there for now. Have a look at any of those sort of walkthrough videos, and we will carry on with this in the next lecture. Great, thank you very much.